Lecture 6. Lecture 6. Covariant derivative of a contravariant second-order tensor. In general, in the literature, you see sometimes that this term here is related to the component, okay? Because you call second-order tensor. Tensor is the variant, you see, but contravariant is related to this component, which belongs to here, to the vector space. Okay. Now, since you are dealing with a second-order tensor, this is a tensor. Okay? Don't forget that magic word. This is invariant. See? Now, here is the dual. Okay? This is T. Now, this is lower indices. So this is, in this case, covariant. This is covariant. Okay? And this is the basis vectors. Basis dual vector. Here's the basis vectors. Okay? We're using this here. This is called, as I said, a tensor product. Tensor product. In general, you omit this when we derive. See here, for instance. Now, this lecture 6 will concentrate, okay, on this red mark here, okay, for the attention now for this contravariant components, okay. In lecture 6, we're going to develop this covariant component. This contravariant component belongs to the vector space. This one belongs to the dual vector space. Just look at this figure. That's why previous lectures, they are important for you to follow, okay, step by step. Okay. Now, consider the covariant derivative. Covariant derivative, you see, the term covariant, this is Ci, okay? I is upper, but it is in the denominator. So I here is called covariant. Okay? Now that's why a covariant derivative. Now I will apply the same as we did before for a vector. Okay? So first order tensor. Then you just expand this. Okay? Now that's important. The order is quite important. Okay, you must expand, just maintaining the order. You see, J comes first. You see, this partial derivative, J comes first. This partial derivative, J comes first. You see, the order here is quite important. Now, we saw the definition of this partial derivative here. See? Attention. Two free indices, okay? Both are lower indices. I is lower and J is lower. You see here? Left hand side, two free indices, okay? Right hand side, two free indices. So this M, that's a dummy. Likewise, the same over here, okay? You see K and I, these are free indices on the left hand side and the right hand side. N is dummy, okay? Now I'll just substitute this relation 2 into 1. That's easy, okay? Just a substitute. Now, I want of this term here, since in this case, M is dummy and N is dummy, okay? So I can enforce, okay, this here to swap, okay, just such that I'll get the same AJ, AK, as we did for the first order. Fortunately, this M here is dummy, and this m is dummy. I just exchange. You see, k is already on the right here, so I just put j here and j here. Okay. Now you can see here. That's quite easy. Okay. J here and j here. Okay. Now k is already here, so I maintain this term here. Okay. I want the first one is j. It's okay. The second one, I'll change here n by k, but there is a k here. So because it's dummy, I always change here. So you just look at here. It's quite easy, no problem. Now I obtain what I want. Aj, ak, aj, ak, aj, ak. See clearly. Okay. Now always remember that you can swap this partial derivative here. Okay, because this will be a second derivative and this will be second derivative, as we did before previously. So this ensures that the Christoffel symbols of second kind is symmetric with respect to ij. Ij is equal to ji. This comes from here. Okay, just a symmetric in I and j. I can swap. Okay. Now, in terms of components, now I can work only with the components. Okay. This is the basis. Don't forget the basis. Okay. I can omit, no problem. So I just copy from here to here. Just look at that. I just copy. You see, these are components, okay, of the covariant derivative of a contravariant component. Just look clearly. Okay, I will finish here, and then lecture 7, I will derive exactly as we did here for the covariant component. Okay, this will be covariant component.